Hello and welcome to my presentation on introducing mathematical thinking, assignment 2. Today we're going to be talking about the Königsberg puzzle as presented within this assignment. The puzzle is, can each landmass be visited by crossing each bridge only once? So we try and find that out through trial and error. We realize that no matter what way we go about it, either bridge 3 can't be crossed or bridge 7 can't be crossed. So there seems like there is no solution. So in order to try and find a solution, I added some letters to indicate the different land masses, and then the bridges are obviously already numbered, just to figure out if there's a sequence of some sort or a common rule that can essentially help us find a solution for this. So we simplified the following diagram. So the letters indicate the land masses, the lines indicate the bridges, and color coding is added for visual ease, just because it looks pretty really. And so now a common rule really needs to be found if we're going to figure out whether Königsberg can be solved or not. So for example, I take this simple square representing 4 land masses. Each landmass has 2 bridges connected to it. This is represented by the 2 next to each letter, as like seen in B, A, C, and D. This shows that there is currently 4 landmasses with even number of bridges. Everything contains 2's, which is an even number, and there are no landmasses with odd numbers. So our assumption from this example can be, as long as there's no odd numbers, like no landmasses with odd numbered bridges, then it seems like there will always be a solution. So therefore, each landmass can be visited by crossing each bridge only once, and this is indicated as the arrows show. I mean, it can be done any way with this example. You can do it the reverse way as well. So far we've come across the common rule, or the common rules that we've developed are each bridge can be crossed only once if there are 2 or more land masses with an even number of bridges connected to them. This can actually technically be 1 as well, just as long as there's even number of bridges. That's the main important note, as well as each bridge can be crossed only once if there are no land masses with an odd number of bridges connected to them. So we add a bridge between C and D just to, I guess, make the puzzle a bit more complicated. And as you can see, starting from the landmass D, going up to B, to C, down back to D, A, and then back to C, this is actually solvable. So this time there are 2 landmasses with an odd number of bridges, C and D, and there are 2 landmasses with an even number of bridges, A and B. So, however, another rule that I figured out when trying to do this, if you try and start from a landmass that has an even number, it's actually unsolvable. So, as shown there, there's always 1 bridge that's left over. So, on top of the rules that we had earlier, we've now developed another rule. If 0 or 2 landmasses have an odd number of bridges connected to them, then the person traveling across the bridge must start on the landmass with an odd number of bridges connected to it. As well as we've also further developed on the rule that either 0 or 2 landmasses have to have an odd number of bridges connected to them. From here we further complicate the example, and this starts to look a little bit more like the Königsberg one. There's 4 land masses with odd numbered bridges connected to them. So we try and solve this one, and it seems that no matter what sequence we do, it simply can't be solved. You try it one way, there's always 1 bridge left over, and that just sort of helps further prove these points that I've just developed. Let's apply those points to the Königsberg bridge puzzle. The number of bridges that each landmass contains has been added beside the letter representation of the landmass. So C has 5 bridges, D has 3, B has 3, and A has 3. So given the fact that this is very similar to the previous example, which also contains 4 land masses with an odd number of bridges connected to it, then we can start to understand that these rules probably are in fact true. And so by using that, we can see that, as shown here, as each movement across each bridge occurs, it's very similar, leaving one bridge left out. So therefore, by applying the previous developed rules to the Königsberg puzzle, the rules are proven correct. Therefore, if one bridge is removed from either one of these examples, as shown here, then two land masses have an even number of bridges, 4 and 2, as shown in C and D, while the other two land masses have an odd number of bridges, 3 and 3, A and B, and therefore that can be solved. So that further proves these points that I've just pointed out. So this is a further representation of what's just occurred from that simplified form, where if we look at this, we can solve this puzzle now just by removing one of those bridges. And the same, it doesn't necessarily have to be that bridge in particular, it can be any bridge really. The other thing to note is that if one bridge is added as well, as long as there are only 2 or 0 land masses with odd numbers, then the puzzle can be solved. So as shown here, just by adding a bridge, A and B go from having 3 bridges to 4 bridges connected to it, meaning that there are two land masses with evenly numbered bridges. And then same with B and D, there are now 2 land masses with evenly numbered bridges and 2 that are odd, therefore making it solvable. Thank you for watching my presentation.